So in this video, we're going to continue our discussion of L'Hopital's rule, and we're going to look at examples that have a different form than our last video. We're going to look at forms of infinity over infinity and see how we can use L'Hopital's rule for those. If we look at our first example, we have the limit as x approaches infinity for 4x squared minus 3x plus 5 over 3x squared plus 2x minus 1. So if I start by substituting in infinity, I'm going to notice that I'm going to get 4 times a large number squared, which would be larger, minus 3 times a large number plus 5. So everything in the top is approaching infinity. On the bottom, in the denominator, if I do the same thing, as x approaches infinity, 3x squared is going to be very large. Then I'm going to add another large number and subtract 1. So that is also approaching infinity. So I see that I have the form of infinity over infinity. Well, L'Hopital's rule applies to this, just like as our previous problems where we had 0 over 0. And what I can do is take the derivative of the numerator and the denominator and then try my limit again. So I would get the derivative of 4x squared would be 8x minus 3. Then on the bottom I would get 6x plus 2. Now as x approaches infinity, I'm going to again get that indeterminate form of infinity over infinity, which says, well, I can just take the derivative again. And as x approaches infinity, on the top I'm going to get 8, and on the bottom I'm going to get 6 when I go ahead and take my derivatives again. But then I know that that simplifies down to 4/3. So that would be my answer for my limit. Now let's look at another example. We have the limit as x approaches infinity for the natural log of x over 2 square root of x. So again, as x approaches infinity, the natural log of x would go unbounded because we know that the natural log graph continues to grow as x approaches infinity. On the bottom, we would have 2 times the square root of a large number, which also would be a large number. So we'll try taking the derivative of our numerator and denominator and see what happens there. So if I take the derivative of the numerator, I get 1 over x. In the denominator, I have 2 times the derivative of x to the 1/2 is 1/2 x to the negative 1/2. But that's going to give me, now let's make sure we leave ourselves plenty of room here. The limit as x approaches infinity for 1 over x. And then the 2 and the 1/2 will cancel each other, and I get 1 over the square root of x. But dividing by the square root of x is the same thing as multiplying, or dividing by 1 over the square root of x. Is the same thing as multiplying by the square root of x over 1. So really, I have the limit as x approaches infinity for the square root of x over x, which would then simplify to 1 over the square root of x. So after quite a bit of algebra there, we can get this simplified down to the limit as x approaches infinity of 1 over the square root of x. But that's going to be 1 over a very large number, and we know that when that happens, our limit is approaching 0. In our last example, we're going to find the limit as x approaches infinity for e to the x over x squared. So as x approaches infinity, we get infinity on the top, infinity on the bottom. So let's take a derivative of numerator and denominator. So I have e to the x over 2x. But again, if I let x approach infinity, I get infinity over infinity. So we'll take another limit. And when I do, I'm going to take the derivative of the numerator and the denominator, and I get e to the x over 2. But as x approaches infinity, e to the x goes towards infinity, but the denominator is 2. But if I have a very large number divided by 2, that's still going to approach infinity. So for this example, our limit would be infinity.